In section 11.4, we discussed the membryless Gaussian channel. Why do we study the Gaussian channel? The Gaussian channel is the most commonly used model for a noisy channel with real input and output for two reasons. First, the Gaussian channel is highly analytically tractable. And second, the Gaussian noise can be regarded as the worst kind of additive noise subject to a constraint on the noise power. This will be discussed later in the chapter. We first define the Gaussian channel. A Gaussian channel with noise energy n is a continuous channel with two equivalent specifications. First, it can be specified by the conditional PDF Fy given x, which is a Gaussian distribution with mean x and variance n. And second, it can be specified by the noise random variable z, which is a Gaussian random variable with mean 0 and variance n, and the output of the channel is equal to the sum of the input x and the noise random variable z. This is illustrated in the following figure. Accordingly, we can define the membryless Gaussian channel. A membryless Gaussian channel with noise power n and input power constraint p is a noiseless continuous channel, with the generic continuous channel being the Gaussian channel with noise energy n. The input power constraint p refers to the input constraint kappa p, with kappa x equals x squared. That is, the cost for transmitting a signal is proportional to the energy of the signal. Theorem 11.21 states the capacity of a membryless Gaussian channel. The capacity of a membryless Gaussian channel with noise power n and input power p is equal to 1/2 times log of 1 plus p over n, and the capacity is achieved by the Gaussian input distribution with mean 0 and variance p. This is the main theorem in this section. Here are a couple of remarks. From the above formula, we see that the capacity of a membryless Gaussian channel depends only on the ratio p over n, called the signal-to-noise ratio. Observe that the capacity is strictly positive no matter how small the signal-to-noise ratio is. It is because the logarithm is always greater than 0. When there is no input power constraint, that is, when p is equal to infinity, the capacity is infinite. Lemma 11.22 is instrumental for proving the capacity of a membryless Gaussian channel. Let x, y, and z be real random variables, and y is equal to x plus z. Then the differential entropy of y given x is equal to the differential entropy of z given x, provided that the conditional PDF f z given x exists for all x in the support of x. This lemma says that, conditioning on the random variable x, the conditional differential entropy of y is equal to the conditional differential entropy of z. This lemma also holds when x, y, and z are discrete random variables, with differential entropy replaced by entropy. This is obvious because conditioning on x, y, and z determine each other, and so the conditional entropy of y given x is equal to the conditional entropy of z given x. However, this interpretation does not apply to the continuous case, because differential entropy does not measure the amount of information contained in a continuous random variable. Here is the proof of lemma 11.22. Assume that the conditional PDF fz given x exists. Now consider fy given x evaluated at y given x, This is equal to fx plus z given x evaluated at y given x, because y is equal to x plus z. Now, conditioning on the events that the random variable x is equal to small x, we can replace this random variable x by the constant small x. In the next step, we subtract from the random variable x plus z the value small x, and we subtract the same value from the parameter y. This step is justified by the observation that for any random variable w, fw of small w is equal to fw minus c evaluated at w minus c. That is, the value of the PDF does not change if we shift the random variable and the parameter by the same amount. Then this small x cancels with this small x, and we obtain fz given x evaluated at y minus x conditioning on x. Thus, we have shown that if the conditional PDF fz given x exists, then the conditional PDF fy given x also exists. Then the conditional differential entropy of y given x equals x is defined, and the conditional differential entropy of y given x is equal to integrating the conditional differential entropy of y given x equals x with respect to the fx of x. Here, y is equal to x plus z, and conditioning on x equals x, we can replace this random variable x by small x. Here, the conditional differential entropy of x plus z is simply equal to the conditional differential entropy of z by the translation property of differential entropy. And this integral is equal to the conditional differential entropy of z given x. This completes the proof of the lemma. We now prove theorem 11.21. Let fx be the CDF of the input random variable x such that the expectation of x squared is less than or equal to p, where x is not necessarily continuous. Since the noise random variable z is Gaussian, the PDF fz exists. Then the conditional PDF fz given x exists and is equal to fz because z is independent of x. From the proof of the previous lemma, we have the conditional PDF fy given x evaluated at y given x is equal to the conditional PDF fz given x evaluated at y minus x given x. Since z is independent of x, this is equal to fz of y minus x. Thus, we have shown that fy given x of y given x is equal to fz of y minus x. And by proposition 10.24, the PDF of y, fy of y, is equal to integrating fy given x of y given x dfx, regardless of the distribution of the input random variable x. Therefore, the PDF fy of y exists, and hence, the differential entropy of y is defined. Now consider Ixy equals the differential entropy of y, which we have shown to exist, minus the differential entropy of y given x, which can be determined from fy given x. Now by lemma 11.22, hy given x is equal to hz given x. And hz given x is equal to hz because z is independent of x. Now the expectation of y squared is equal to the expectation of the square of x plus z, which can be expanded into expectation of x squared plus expectation of z squared plus 2 times the expectation of x times z. Now the expectation of x times z is equal to the expectation of x times the expectation of z, because z is independent of x. And because z is zero mean, expectation of z is equal to 0, and so this term goes away. By the input power constraint, the expectation of x squared is less than or equal to p, while the expectation of z squared, that is, the variance of the noise variable, is equal to n. Therefore, the expectation of y squared is less than or equal to p plus n. Then by theorem 10.43, the differential entropy of y is less than or equal to 1/2 times log 2 pi e times p plus n. With equality, if y is the Gaussian random variable with mean 0 and variance p plus n. This can be achieved with the input random variable x being Gaussian with mean 0 and variance p. To see this, we consider the random variable x being Gaussian with mean 0 and variance p, and the noise variable z being Gaussian with mean 0 and variance n, which is independent of x. And so the variance of y is equal to p plus n, and obviously the mean of y is equal to 0. Because y is equal to x plus z, the sum of two Gaussian random variables, y is also Gaussian. Therefore, y is the Gaussian random variable with mean 0 and variance p plus n. In step 4, we have ixy equals hy minus hz, where hz, the differential entropy of the noise variable, is a known quantity. Therefore, to compute the channel capacity, we need to maximize the differential entropy of y. Hence, the channel capacity, C of p, is equal to the supremum of h of y over all input distributions f of x, such that the expectation of x squared is less than or equal to p minus h of z. Where this supremum, as we have seen, is in fact a maximum equal to 1/2 log of 2 pi e times p plus n, and h of z is equal to 1/2 log 2 pi e times n. Combining the two logarithms and cancelling the 2 pi e's, we obtain 1/2 times log of 1 plus p over n. This proves the capacity of a memoryless Gaussian channel.